Electronic devices is a pure VLSI front end. It breaks the black box by revealing how transistor fabrication and physics directly control analog accuracy and digital speed, leakage and scaling. So electronic devices make analog and digital circuits possible. So hi dear students, namaste. This is SMM Trinath, the faculty of ACE Engineering Academy. So dear students, so welcome to ACE Engineering Academy and ACE online platform and this GATE 2026 Booster Series, and welcome to all the aspirants who are preparing for the GATE 2026. And in this, the special program of one hour, our main context here is the NAT questions and multiple select questions, which is absolutely, I think, going to boost up the confidence levels for the students who are preparing for GATE 2026. So guys, let us try to do a lot of decoding concept for the given question. Let us try to become a master in both numerical and conceptual problems, and let us challenge yourself with 1 hour of focused practice. Okay guys, I hope you people preparing fantabulous for the GATE exam, that is in the subject of electronic devices, as it is very, very important in the front end VLSI. Okay, let us see some sort of standard questions, my dear boys and girls, and I am expecting you people will be solving with me, and I'll be giving you some time. I'll wait for your answers. If you're not getting any answers, of course I'll be showing you in the classroom in here itself, but still you please put pen on the paper, ready with the calculators, ready with your book and pen. Try to solve parallelly with me, dears. Okay, let us see in this 1 hour how many questions we can conclude. Okay, let us have a look carefully. The very first question, which is so called MSQ question. Students, if you check it out here, consider the recombination process via bulk traps. Underline the word carefully, traps. So especially in case of fabrication, as I discussed a lot in the classroom, in case of fabrication, these play a very vital role. Am I right? The trap density for silicon, it is almost like a 10 power 15 per centimeter cube. Am I right here? 10 power 15 per centimeter cube, which is almost equal to moderate doping, above light doping and below moderate doping, like that. Anyways, dear students, so consider the recombination process via bulk traps, and in the forward biased PN homojunction diode, the maximum recombination rate is Umax. Okay, fine. If the electron and hole capture cross sections, they are equal. Okay, fine. Then which one of the following statements are true? Dears, whenever you are thinking about the trap, try to understand a point carefully between conduction band to valence band. For example, dear students, let me say y-axis we have energy and x-axis say it is a distance. Am I right? So if it is EC and this is EV, so electrons in the conduction band recombining with the holes in the valence band. I repeat, electrons in the conduction band, if they recombine with the holes in the valence band, it is technically called band to band recombination. Excuse me, am I right? Band to band recombination. Next, now understand there exist a huge traps. There are huge traps in the given body. So a lot of trap energy levels will be existing. Lot of traps, which is for sure. And in that case, every trap, every trap energy level will be having density of states. Am I right? Now, if an electron here is getting recombined with the trap states, electron here is getting recombined with the trap states, then that type of recombination, technically we call them as SRH, Shockley-Reed Hall. Shockley-Reed Hall. For example, if it is a band to band recombination, it is delta by tau. That's a simple, formulae we have studied a lot. It's a band to band recombination. If it is a Shockley-Reed Hall recombination, SRH recombination, U is equals to, you'll be getting 1 by tau into N dot P minus Ni square whole divided by N plus P plus 2 Ni. Am I right, everybody in the class? This is what we will be getting if I consider SRH recombination. So this question is purely based on SRH, Shockley-Reed Hall. And also try to recollect why we are getting recombinations. Simple logic. Electrons should lose energy. Once it lose energy, they can easily recombine or they can easily fall from higher state to the lower state. Am I right? what is the probability that a particle can lose energy in the forward bias if there exist a huge collisions, am I right? If there exist huge collisions, then particles will be losing energy. So if I say examiner clearly specified it is under forward bias, clearly specified it is under what here forward bias. You know, dear students, in case of forward bias, you know, for example, let me say it is a depletion region, you know, it's a junction. Say this is N side, it is P side. So here we have positive ions, am I right? Depletion region, positive ions N side and a negative ions P side. True or not? Therefore here there exists electric field, so called built-in electric field, am I right here? Or we say junction electric field, and yes, you can take it as a junction electric field, whereas this is the junction force acting on the particles. So in the forward bias, if I provide an external force in this way, this is external force acting on electrons. Let me say this is an external force acting on electrons. Now due to this, let an electron is moving forward, and this is the force which is trying to make this electron, you know, oppose, right? So it try to move back, move forward, 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 move back. That means there exist a huge collisions. Am I right, dear students? There exists what here huge collisions, and there exists an bipolar transport over here. A huge collisions exist. Due to that, it lose energy, exchange of momentum, that is so-called scattering. Then no doubt they try to jump from higher level to lower level. So depletion region is a region where probability of recombination is very high. Similarly, in the reverse bias, probability of generation is very high. Am I right, dear students? So all these cases we are supposed to consider in the depletion region. So when you hear the word trap, your mind must be recollecting this context. I hope you got the point here. Of course, it might be 1 mark or anything. You try to recollect the context, what exactly we have discussed when you hear the word, trap. Right, yes, anyways, come back. So, which of the following statements are true? It is MSQ. Which of the following statements are true? Please go through this, dear students. Which of the following statements are true? Any students has given the answer? Yeah. No, they are showing that it is low volume, it seems. It is okay? Okay, fine. Right. Okay, fine. I think now volume is increased here. You please check it out, live batch. Okay. Now anyways, students, what exactly they have given? I am waiting for your answer, dear students. Meanwhile, you please try it out. The option A representing Umax. Umax depends exponentially on the applied bias, and the Umax occurs at the edge of depletion region in the device. And with all other parameters unchanged, Umax decreases if the intrinsic carrier density is getting reduced, and with all other parameters unchanged, Umax increases if the thermal velocity of the carriers are getting increased. Very fine. Anyways, dear students, let us try to decode it clearly, carefully. Okay. So, students, let me take our PN junction. Say, guys, this is N side. Okay. And this is a P side. Okay, dear students, and here N type contains what ions, dear students? Positive ions, and here negative ions. Am I right? Hope you know that. Assume that it is an abrupt junction. It is an abrupt PN junction. That is a step graded PN junction. In that case, the volumetric charge density distance, then you will be getting the volumetric charge density in this way. Am I right? So it is plus and this is minus. So from here, could I get electric field profile, dear students? Could I get electric field profile? So from Poisson's equation, there you can easily get electric field is nothing but what here? Minus, otherwise directly you can tell. So it is nothing but integration rho v by epsilon dx. Am I right? That is nothing but electric field. So if I go for integration of this, we are very happy to say it is like a triangle. And this is the place exactly we get electric field max, E max. Everything is happening in the depletion region. Please note this point. Okay, take care. That means depletion region is the region where there exists a huge scattering. Depletion region is the region where there exists a huge electric field at the junction. Therefore, what do you mean by that? The junction force is very high at the junction. At the junction force, what I have discussed just before, this junction force is very high at the junction. Due to that, a huge scattering exists. Due to that, SRH recombination is very high near to the junction. And as electric field is getting decreased, SRH recombination will be falling down if I move away from the junction. So, if I sketch X with the y-axis as SRH recombination rate, it is almost like this. It is almost like this. That means it is very high near to the junction, and if I move away from junction, it will be getting decreased. So it is almost representing Umax. Representing what, dear students? Umax. SRH recombination rate, maximum recombination rate. Is it okay, guys? So this is what we understand from decoding the concept. Now in the similar way, if I go for energy band diagram over here, so the same case, same diagram, this is N side, okay, and it is what, dear students? P side, right? So here we have positive ions and here negative ions, right, dear students? So at equilibrium, the Fermi level, there is no slope in the Fermi level, and no doubt here, otherwise do one thing, directly we can go ahead. So the energy band diagram will be in this way. True or not, dear students? The force is in this direction, therefore the energy band diagram is in this way. Now here I am supposed to consider the traps. Traps exist everywhere, but the place where the particles are losing energy levels. The particles which are losing energy, where there exists a huge scattering, that is the place where exactly I am taking the traps. I think whenever I provide a forward bias, because of the forward bias, the carrier, because of losing its energy, they can easily recombine with the trap levels. Am I right, dear students? They can easily recombine with the trap levels. So Umax is very near at the junction. True or not? Now let us enter into the answer. And also, what is the formula you have, dear students? In forward bias. In forward bias. Respond, dear students. What is Umax? Umax is simply equals to, whenever I say forward bias, N dot P is simply equals to, Ni square into exponential diode voltage by Vt, which is a mass action law. Am I right? This is the mass action law under forward bias, because N dot P is greater than Ni square. True or not? Then 1 by tau into what I'm going to get? N dot P minus Ni square whole divided by N plus P. That's it. So if you could solve, you're going to get Umax proportional to exponential, diode voltage by 2 Vt into Ni by 2 tau. This is what you're going to get. Excuse me, correct? It is nothing but like eta Vt, right? Eta Vt. Okay, now go through the first question, first option, dear students. Umax depends exponentially on the applied bias. Yes, I think this is perfect. Umax strictly depends on the diode voltage, and that dependency is exponential. So option A is true. Option A is true. Am I right, everybody in the class? In the similar way, go through the second one. Umax occurs at the edges of the depletion region in the device. No. It is not exactly occurring at the edge, dear. Why? Because it is maximum at the junction, and moving away, the Umax is getting decreased. So option B is false. But examiner is asking which of the following options are true. That is what we need to find. Am I right? Now, third, with all the other parameters are unchanged, Umax decreases if the intrinsic carrier density is getting decreased. Okay, have a look carefully, guys. Now, Ni, Umax strictly depends on Ni. So if Ni is getting decreased, Umax is getting decreased. Perfect. So option C is again true statement. So last but not least, option D. Go through that, dear students. With all other parameters unchanged, Umax increases if the thermal velocity of the carriers are getting increased. Students, I hope you know thermal velocity. Students, whenever I say thermal velocity, it is nothing but what, here? Average collision length by average collision time. So let me say a number of collisions are more. If collisions are more, tau c will be small. Excuse me, right? Tau c will be small. That means in the small time period, in the small time scale, okay, there exists a huge number of collisions. Because of that, for sure thermal velocity is getting increased, and whenever in the short span of time, if collisions are more, there exists a huge scattering by which the probability of recombination is very high. So lesser the tau c, higher the thermal velocity, lesser the tau c, higher will be the Umax. So I think that is what he is asking. So with all other parameters unchanged, Umax increases if thermal velocity is increasing. Perfect. This is a true statement. So I think option D is also true. So option A, option C and option D, all the three options are true for this given question. Hope you got understood or not, dear students? Everybody in the class? Right. I think voice is clear. Students who are in the live, I think voice is clear. Ima Prasad, voice is clear? Voice is clear? Can you switch off this AC, dear? Right. Anyways, thank you so much, dear students. Let's enter into the second question. Have a look carefully, my dear boys and girls. A Zener diode is subjected to an applied bias VA. Okay, this is examiner specified, it is a Zener diode, and is subjected to the applied voltage VA as shown in the figure. First of all, by seeing the statement, if I go through this, for example, this is the PN junction examiner has specified. Am I right, dear students? This is N, this is P, and this is a diode voltage. Here diode voltage is nothing but VA. Am I right? See here, diode voltage, I am representing it as VA because examiner has given it as a VA. So as per the polarities, this is given minus, this is given plus. So if the layman watch this, then absolutely what he understand, anode voltage greater than cathode voltage. Anode voltage greater than cathode voltage clearly represents it is a forward bias. Okay, fine. As per the first sentence what we have studied. Okay, now let us enter into the next. If the total junction voltage is 5 volt, this is amazing here. Junction voltage is 5 volt. I hope you remembered this. What is junction voltage formulae? Vj is nothing but Vbi minus Vd. This is universal, am I right? Where diode voltage is 0 in open switch, or we say equilibrium. True or not, dear students? In open switch or equilibrium. Therefore, junction voltage will become built-in voltage under open switch or equilibrium. In the similar way, diode voltage will be positive in forward bias. If it is forward bias, then in that case, Vj is nothing but Vbi minus of plus diode voltage. True or not? In the similar way, diode voltage is strictly negative. If I go for reverse bias, because it is in the third quadrant, reverse bias characteristics of a diode. In that case, this is what, dear students? In reverse bias. Therefore, what is Vj? Vj is Vbi minus of minus diode voltage. This is what you need to follow, because universally Vj is nothing but Vbi minus Vd. So here, where I was surprised by seeing this question, the junction voltage examiner given as 5 volt. So how crazy this is. It is a very large voltage, man. The 5 volt at the junction itself is a very large voltage. So with a minimum common sense, we can understand, I think depletion width is large. Because in the reverse bias, at the junction itself 5 voltage there indicates. I hope depletion width might be large. Why? Because built-in voltage, commonly it will be very small, in the order of 0.3 volt or 0.5 volt like that. Now the junction voltage is 5 volt indicates, might be external force supporting the built-in force. If external force supporting built-in force, it must be reverse bias. But here, it is showing that it is in the forward bias. So something fishy here. Okay, so relax, let us not have any conclusion that whether forward bias or reverse bias. Let us try to decode in a proper way. Fine. Now determine the value of applied voltage. That means the diode voltage we need to find. And also identify the mode in which the diode is biased. It is again MSQ. He is asking about the diode voltage value and in which mode of operation it is getting operated. And the equilibrium energy band diagram. So this is the band diagram. Examiner has given the band diagram over here, which is under equilibrium it seems. Very nice. So guys, let us have a look carefully. So first of all, if I go with the band diagram, y-axis is energy and x-axis distance. So equilibrium indicates there must be no slope in the Fermi level, am I right? And yes. This is what he has given, am I right, dear students? This is what examiner has given, and this is EI. So it is what here, EC, it is EI, it is EV, it is a Fermi level. Now what exactly examiner has given? This difference is 0.2 electron volt. So this difference 0.2 electron volt, and this difference is 0.3 electron volt. That means this difference is a 0.3 electron volt, and this energy gap examiner has given as 1 electron volt. Now respond, my dear boys and girls, if that is 1 electron volt, then this will be 0.5 electron volt. In the similar way, this is a 0.5 electron volt. I hope you know from equilibrium band diagram, in this formulae, what I could find, I think I could find built-in voltage, because examiner is asking to find a diode voltage. A junction voltage examiner has given. So the only unknown quantity for me is a built-in voltage. So I think from equilibrium band diagram, we can easily measure the built-in voltage. That's what we need, right? So how can I find built-in voltage? I hope you know this. The height of the slope is nothing but Q times VBI, because under open switch, it is a Q times VJ. Under open switch, VJ is nothing but VBI. So this height I need to find. That means this height I need to find. So if I know this and if I know this, I hope that is nothing but VBI. I hope now it is very simple mathematics, dear students. Please let me know, boys and girls, if it is 0.2 and this is 0.5, I think this will be 0.3 electron volt. Excuse me, true or not, everybody in the class? In the similar way, this is 0.5, this is 0.3, then I understand it is 0.2 electron volt. So from here, I am very happy to say Q times VBI is nothing but this plus this. So 0.2 electron volt plus 0.3 electron volt. So 0.2 electron volt plus 0.3 electron volt, which is simply equals to 0.5 electron volt. Therefore, VBI is simply 0.5 volt. Fine. Now, what are the universal expression for junction voltage, dear students? Junction voltage is nothing but VBI minus VD. This is universal expression. Universal expression, not forward bias, not reverse bias like that. It is a universal expression, right? Now, what are the junction voltage examiner has given? 5 volt. Now, respond, dear students. What junction voltage examiner has given? It is simply 5 volt. And the built-in voltage, just now we got it as a 0.5 volt minus VD. Therefore, if I measure VD, I am happy to say 0.5 minus 5, which is a minus 4.5 volt. Oh my God. That means the diode voltage what I got here is a minus 4.5 volt. Excuse me. That means what? That means what? If I go with the polarity, see, as per the polarity, what exactly examiner has given, see here. Respond, dear students. So this left side is N, right side is P. So this is N and this is P. Now this is what examiner has specified. Am I right? And what he has given, this is, this is plus, this is minus, is a diode voltage, which is early voltage. I'm sorry, VA, sorry, it's a VA. And this value, I got it as a minus 4.5 volt. Indicates I need to reverse the polarity. Excuse me, right? As per the polarity specified by the examiner, if I got it as a minus 4.5, I need to reverse the polarity as per the solution. That means this will become positive, that will become negative. Indicates cathode voltage greater than anode voltage. Clearly represents it is a reverse bias. It is what here? Reverse bias. Wonderful. It is not forward bias. It is reverse bias. I hope you got the point, dear students, everybody in the class. So answer is reverse bias and a minus 4.5 volt. It is not plus 4.5 volt, it is minus 4.5 volt. Hope it is very easy question, but the only thing is there might be chances that students getting confused or students will take a wrong decision that it is a forward bias. Take care of that, my dear students. Even though for multiple select questions you might be not having negative marking, but why should we lose even 1 mark? Okay, 1 or 2 marks. It's very important for the competitive exams, right, dear students? Now anyways, I hope you students are trying. Yeah, Rakesh, you kept it as a 4.5. It is minus 4.5, dear. And Rakesh, you said reverse bias. I'm very happy. You're fine. Fine, dear. Fine. Very good. Very good, Rakesh. And I'm waiting for other students also. You students need to give reply. Okay. Put pen on the paper. Okay, dear students. Anyways, let me move towards one more interesting question. Have a look carefully, guys. The MOS CV characteristics are given below. Okay. CV characteristics are given below. Students, just watch here and could you please let me know, by seeing these characteristics, examiner clearly specified it's a CV graph. Could you please let me know, is it for NMOS or PMOS? I mean to say, the substrate is what? P substrate or N substrate? Anybody in the class? Yeah, still voice is low it seems. Can you please check it out here? Voice is low it seems. Voice is clear? Are you sure? Right, right. Yes, boys and girls, could you please let me know? Yeah, wonderful, Rakesh. Thank you so much. Yes, Winky, you're right, you're right. Yes. No, Aditya, you're saying that even though it is a Zener diode, can I take reverse bias? Aditya, you can't take like that. If examiner has given it as a Zener diode, there is no rule that it must be under reverse bias. You need to go for the back test. Take care of that, okay? And right, yeah, Amen, you're right, P substrate, you're right, P substrate. It's a P substrate. And it is very clear to say that left side is what here? Accumulation mode of operation. And here, you know, a small flat band going to be started. And this is a depletion. And it is like a threshold voltage. And here it is inversion. Initially it is a weak inversion, next is a strong inversion. And the characteristics are not getting increased, it is maintained constant. It clearly represents it is a C minimum. C minimum indicates this must be high CV characteristics, high frequency. It is not a low frequency, high frequency CV characteristics. Examiner has not given anything, but by seeing the graph, your mind should give you the answer. That's a beauty of preparation for this competitive exams called GATE exam or engineering services. Correct or not, dear students, right? Now come back. Epsilon R. Examiner has given epsilon R, relative epsilon he has given for silicon and silicon dioxide. Then we need to find depletion width max. Depletion width max indicates what? It is in the silicon. And width of silicon dioxide, that is a TOX, TYX. Width of silicon dioxide is what here? TYX. That means what we studied here, it is like this, XD max by TOX. This is what examiner is expecting answer, which is a NAT question. Okay, it's a very easy question, right? So anyways, students, by seeing this question, it is very clear that COX, because in accumulation mode of operation, the fixed capacitance is COX, which is a 12 microfarads. Excuse me, true or not? And also, this is nothing but what, dear students? The maximum capacitance, but it is simply COX. And what is C minimum, dear students? C minimum is nothing but, you know, capacitors are in parallel, capacitors are in series, C1, C2 by C1 plus C2. That means what? You know, COX into C depletion minimum. Am I right, dear students? C depletion minimum by COX plus C depletion minimum. True or not, everybody in the class? So what is C minimum here? That is nothing but 3 microfarads. Now respond everybody in the class. So 3 micro is equals to 12 into C depletion minimum whole divided by, you know, 12 plus C depletion minimum. Okay, I hope from here you can easily measure the value for C depletion minimum. So can anyone tell me what is C depletion minimum you got, dears? Can anyone tell how much you got C depletion minimum? Students who are in the live YouTube, what's the value for C depletion minimum you got? Anybody in the class? How much you got, dear students? Otherwise, I can show it. You got 4 C depletion minimum. So Wonderful, dear. You're right. Absolutely. So, like Mansoor and Saji, Neville Saji. You're right. You're right. It is a 4 microfarads. Perfect. So, C depletion minimum is a 4 microfarads. Your students got. Now, could you please let me know, dear students? Now, what exactly we need to find? XD max by torques. Am I right? Therefore, C depletion minimum by cox. Can I divide like this? What is the formula for C depletion minimum, dear students? Epsilon naught, epsilon r of silicon into area whole divided by XD max by, what is cox? Epsilon naught, epsilon r of silicon dioxide into area by torques. Excuse me, true or not? And this value, C depletion minimum just before your friends got, it is a 4 microfarads. And cox value is nothing but what here? 12 microfarads. True or not, dear students? Now what I'm going to get here, so if I could nullify epsilon naught and area, what I'm going to get here, dear students, it implies, so right, dear students, epsilon r of silicon whole divided by epsilon r of silicon dioxide into torques by XD max is equals to 1 by 3. I hope epsilon r of silicon dioxide examiner has given. Am I right, dear students? So finally, if we could solve torques by XD max, what exactly we need to find, dear students? XD max by torques, not dear. Okay, just if I could solve, therefore XD max by torques. So anybody in the class? What is the answer exactly you got? XD max by torques. I'm waiting for you. XD max by torques. How much you got, dear students? XD max by torques. How much you got, dear students? I hope you guys are trying. Okay, keep engaging your mind, man. Okay, don't sit idle. Yeah, wonderful, wonderful. Rakesh, you got 0.8. So, no Rakesh, no Amen. Others, you please try it out. How much is the answer, dears? It is very simple, man. It is equal to 3 into 3 by 2. Am I right, dear students? What exactly examiner has given here? It is a 3 by 2. Epsilon r of silicon by epsilon r of silicon dioxide is 3 by 2 now, dear students. So it is simply equals to what here? 3 into 3 by 2. So I understand the answer for the given question is 4.5. 4.5. So the ratio for the given question is simply 4. You're right, you're right. So Rishindra Reddy, you're right. 4.5 is perfect, perfect, perfect. Good man, good. Others, it's okay, fine, no problem, no problem. Keep trying, keep trying. Okay, right. Let's move to one more very interesting question. Have a look carefully, my dear boys and girls. So the BJT characteristics are shown below. Fine, bipolar junction transistor, the output characteristics are shown below. What exactly examiner is asking? So this is one characteristics when IE equal to 0. Have you able to decode it, dears? So x-axis is voltage collected to base and that is collector current. I understand this is common base configuration. Am I right, dear students? Common base configuration. Whereas here x-axis VCE and y-axis IC, that is output characteristics of common emitter configuration. So this is for common emitter. True or not? This is for what, dear students? Common base, and this is for common emitter. Okay. Now, students, by seeing this question, it is very clear to say that this voltage is representing the breakdown voltage, because after breakdown, even the voltage changes is very small, current changes very high. Our voltage is constant, current increases like anything. Am I right? And mainly the breakdown happens at the collector junction. Collector junction is like a I mean, it's a collector to base, the breakdown at a collector to base, light, it's like a normal doping, it's not heavy doping, it's a normal doping. Therefore, it must be avalanche breakdown. Therefore, the avalanche breakdown voltage is nothing but B VCBO. This is for common base, and this is none other than B VCEO. This is for common emitter. Excuse me, okay, fine. Now, if alpha F is equals to alpha DC is equals to 0.98, examiner has given, and empirical constant N is 2.5, then what is Vx? Very fine. That means examiner is asking us to find B, VCEO. B VCEO, that is what we are supposed to find. I hope you know the relation between B VCEO and B VCBO. Remember or not, dear students? B VCEO is equals to B VCBO into 1 by beta F whole power 1 by N. I hope you remember this relationship. Whole power 1 by N. True or not? Everybody in the class? Excuse me, have remembered or not? B VCEO is equals to B VCBO into 1 by beta F whole power 1 by N. N represents empirical constant. Am I right? Relation between the breakdown voltages for common emitter and breakdown voltage avalanche, breakdown voltage for common base. I think all the data given by the examiner, and beta F is nothing but alpha F by 1 minus alpha F. I hope from here I can easily measure the value of beta. I can substitute over there all the data given by the examiner. I hope I can easily get the value for Vx. So anybody in the class, can you get the answer? What is the value of Vx you got? I mean, it is not electric field. It is not electric field, it is epsilon. In the previous question, it is not electric field here, it is epsilon. Epsilon. It might be some printing error. It is epsilon. R, he has given R, indicates relative epsilon. Okay, right. Hope you understood, Amen, right? Yes, other students. Yeah. Can I get the answer for this question? Anybody in the class? Let me, I can cross check what answer you got. Is it correct or not? Anybody in the class? Make it fast, dear students. B VCBO, examiner given as 2.5 volt. Beta F, from here you can measure. N value, empirical constant, examiner has given as 2.5. Anybody in the class? Anyways, you try it out, dear students. What answer we have, I am giving that. It is almost like a 5.27 volts. How much, guys? Around 5.27 volts. Is it okay, dear students? That is the value for Vx. That means the avalanche breakdown voltage if I compare with avalanche breakdown voltage of a common base. Clear or not, dear students? This is one more very interesting model. Like that, different models you have. If you can put pen on the paper, you could be getting a tremendous knowledge for sure. Let me go for one more very interesting question. Have a look carefully, guys. In a PN junction diode at equilibrium, underline the word carefully, equilibrium, okay, net current equal to 0. Now, which one of the following statements is true? Okay, following statements are true. Fine. The hole and electron diffusion current components. Examiner is asking about current components, diffusion for hole and electron. Okay, first let us solve everything individually. And clearly, whenever electron and hole drift, electron and hole diffusion, or we say carrier transport, because drift and diffusion both exist at the carrier transport. You remembered why we are getting equilibrium? Why? Because at the PN junction, carriers are getting diffused from high level to low level. That diffusion is creating a built-in electric field. That built-in electric field is creating a force which is balancing further diffusion of carriers, such a way that at equilibrium, drift balance diffusion. That is what we are getting it as a carrier transport. Carrier transport equation, net current equal to 0. Am I right here? Drift plus diffusion equal to 0. Under equilibrium context, we followed. That's the reason why for this question, I am taking the PN junction. And especially only in the depletion region I need to concentrate, because carrier transport equation is strictly valid at the depletion region. Ambipolar transport, continuity equation, carrier transport, Umax, electric field profiles. I think depletion region is like a black box. It's like a magic box, I could say. It's a magic box. Am I right, dear students? Continuity equation, whatnot, everything. Anyways, dear students, so here n type, so let me say y-axis, it is n of x, and x-axis, take it as a distance. In the similar way, y-axis like p of x, and x-axis I say distance. Is it okay, my dear boys and girls? Now respond, dear boys and girls, everybody in the class. Electron concentration is very high in the n side, moving towards p side it is getting decreased, so there is a concentration gradient. Hole concentration is very high in the p side and moving towards left it is getting decreased because of the concentration gradient. So this is representing concentration gradient. Now respond, everybody in the class, because of the natural temperatures electrons are getting diffused in this direction. This is the direction of electron diffusion. So if electrons are getting diffused in this direction, no doubt, then this will be the direction of electron, diffusion current. Am I right, everybody in the class? Direction of electron diffusion current. In the similar way, holes are getting diffused in this direction. If the holes are getting diffused in this direction, then this is the way, the direction of hole diffusion current. This is what here? Direction of hole diffusion current. Because there is no concept of conventional for holes. Now have a look carefully. The hole and electron diffusion current components are in the same direction. Yes, electron current direction and hole current direction are in the same direction. Perfect. So this is true. This is true. What we need to check, what are the statements are true? Yes, this is a true statement. Now check it out here, dear students. The hole and electron drift current components are in the same direction. Hole and electron drift current components. Students, drift current is the direction of electric field. A very simple shortcut, very simple logic. What is the direction of electric field? That is the direction of drift current. Am I right? Now let me know. Electrons are getting diffused from high level to low level. So here I am getting positive ions. And here I am getting what here? Negative ions. Then this is the direction of electric field. If electric field is in this direction, no doubt, this is the direction of drift current. True or not, everybody in the class? Or we can say, drift balance diffusion. So drift must be opposite to diffusion. That's a simple logic. In a similar way here, if I check it out, holes are getting diffused. Indicates here it will be negative ions. Then it will be positive ions. That's what every time here we are getting positive ions in N side, so called depletion, negative ions in P side. You can check it out, you can cross check positive ions and negative ions. Therefore, electric field is in this direction. If electric field is in this direction, no doubt current is also in this direction. Which current? Hole drift current. Excuse me, am I right, dear students? Hole drift current. Because electric field direction, hole drift current will be same, or hole diffusion current is exactly opposite to hole drift current direction. Just I want to show you all the prospects such a way that tomorrow if any sort of question related to this they asked, I think my students need to get a final answer, accurate answer. Right, dear students? Anyways, I think what exactly has given? The hole and electron drift current components are in the same direction. Hole and electron drift current components are in the same direction. True. This is true statement. Perfectly true statement. Third, on an average, holes and electrons drift in opposite direction. Fine. Holes and electrons drift in opposite direction. You can have a look carefully, guys. Students, they are not asking about drift current. They are asking about only drift direction. You can check it out. Students, if electric field is in this direction, then force is in this direction. Am I right? This is the force acting on electrons. So this is the direction where electron is drifting. So this is the direction where electron drift. In the similar way, electric field is in this direction and force is also in this direction. Electric field and force will be same direction for holes. If the force is in this direction, then holes are drift in this direction. Am I right, dear students? So this is hole drift. This is the way holes are getting drifted. This is the way how electrons are getting drifted. I am talking about only direction of electrons and holes. So on an average, holes and electrons drift in opposite direction. Perfect. Perfect. So this is true. On an average, electrons and holes are drifting in opposite direction. Last but not least, on an average, electrons drift and diffuse in the same direction. No, that is wrong. Because drift should balance diffusion. Absolutely wrong. Am I right here? So this is false. Fine, man. So which of the following statements are true? Yes, option A, B and C. Option A, B, C are true. So A, B, C. Mansoor, you're right. Mansoor has given the right answer. And Rakesh, you have given it as B, C, D. No, Rakesh, it is not right. It is not right. Okay, so Rakesh, it is A, B, C. You please have a back test carefully. It is A, B, C. Okay, dear, A, B, C is the right answer for the given question. Guys, okay, good. Let's move to one more very interesting question. Have a look carefully. The following graph shows minority and majority carrier distributions. Minority and majority carrier distributions. Okay, fine. Line A and line B represents what? Very good question. There are two lines. Examiner has given. This is line A, it seems. Okay, fine. And see, there are some dotted lines. This dotted line. Examiner is asking about. It is a line B. He has given as a line B. Now, what exactly line A, line B represents? Options, if you check it out, low level injection, high level injection. My God, very nice question, man. So, anybody in the class? What exactly it represents? Low level injection or high level injection? Very nice question. I'm waiting for your answer. So, how could you justify? By seeing these characteristics, how could you justify whether it is low level injection or high level injection? How could you justify? Are you trying or not, dear students? Okay, fine. Students, I hope you remembered, for example, delta N, we say excess electron density, delta P, excess hole density. In a given body, delta N is always equal to delta P. Let me say it is equal to delta. We represent with an excess concentration of carriers. Am I right, dear students? You know the concept of excess concentration, which is very important. This excess concentration may be due to the forward bias or reverse bias. This excess concentration because of the quasi-equilibrium. This excess concentration may be because of the light, generation of carriers, electron hole pairs, generation due to light, whatnot. Am I right? Now let me know, dear students. Let me say it is, I mean to say p-type, because I hope here it is a base. Examiner clearly specified it is a base. Indicates left side is emitter, right side is collector. It is a base. Then it clearly showing that it is a p-type. In the p-type, students, please let me know. PP naught. PP naught represent what? Majority concentration of carriers. Am I right, dear students? PP naught, and delta. What is the relation between both, if you ask me? Excess concentration of carriers in delta, if it is far less than majority concentration of carriers. If excess concentration is lesser than majority concentration of carriers, then technically we call it as a low level injection. Guys, correct or not? It is a low level injection. Whereas, if excess concentration of carriers, if it is greater than or equals to PP naught, technically we call it as a high level injection. It is called what, dear students? High level injection. This is the low level injection, this is the high level injection. Now, what exactly examiner has given? Students, what we need, let us concentrate only on that. What we need exactly here. See, this is the region and here it is x equals to 0 and x equals to xb. Okay, now this is straight line and he told it is a NB, that means doping in the base. It is what here? Doping in the base. This is representing doping in the base. Then I think it is a PP naught, almost equal to PP naught, because the original formula for PP naught, I hope you know, PP naught is equals to Na by 2, plus root of Na by 2 whole square plus Ni square. Am I right? Charge neutrality principle, right? More precisely, it is Na minus. If no condition is given, 100% ionization, in that case Na minus equal to Na. Similarly, if no condition is given, at the operating temperatures, it is almost equals to Na. That's what we are taking it as Na, NB, Na, base doping. Okay, fine. That means this straight line representing the doping in the base. And this is line A. It is very interesting, Nadias. I'll show you just a minute. This is what line A examiner has given. It is line A. I think it is like a triangle. You're able to understand or not? This is nothing but excess concentration of carriers. I think the emitter base junction is forward bias. Emitter base junction is forward bias. The majority carriers from emitter crossing to the base. Now this is nothing but excess concentration of carriers belongs to emitter. Excess concentration of carriers belongs to emitter. Okay, then it is representing delta. Representing what is delta? The carriers came from emitter to the base. Now this magnitude height, if you check it out, this magnitude height, see this is, I mean to say more precisely, this height is delta. Now happy dear, this height is a delta, exactly delta, x equal to 0. So this height is lesser than this height. So this clearly representing it is a low level injection. This excess concentration of carriers, this height magnitude is lesser than the magnitude of majority concentration. So it clearly representing it is a low level injection. So we are very happy to say it is what is students, line, this is line A. So line A represents low level injection. Line A represents low level injection. Whereas this line B, even it is a triangle, happy. So even here, if you check it out, examiner has given, even it is like a triangle. Am I right, dear students? Right? But if I check it out, this magnitude, delta, I think this magnitude is greater than PP naught. This magnitude, greater than PP naught. That clearly representing this is a high level injection. It is what is students? High level injection. High level injection. So this is nothing but what here? Line B. So line A represents low level injection. Line B represents high level injection. Can you check it out here? Line A low injection. So line A low level injection. Line B low level. No, wrong. Line A low level injection. Line B high injection. Perfect. Line A high injection. Wrong. Line A high injection. Line B low injection. No, wrong. I think it is MCQ, okay, not MSQ, it is MCQ, I understand. So once again, let us cross check again. Line A represents low injection. So line A low level injection, and line B is a high injection. Line B is a high injection. Fine. So option B is apt for the given question. Option B is apt for the given question. Okay, dear students. So please go through these type of questions which are very important. If you could able to solve these questions, indirectly you are having confidence or command in the subject of forward bias, diode current equations, BJT current equations, carrier density profiles, excess minority carrier density profiles, whatnot. Okay, these are a bit tricky type of questions where students need to decode and spend some time to recollect the concept what you studied in your GATE exam. Okay, dear students. Anyways, come back. Let me go for one more very interesting question. Have a look carefully, guys. An abrupt P plus N junction. Examiner clearly told it is an abrupt, that is so-called step-graded junction. Now, it is formed in silicon with Na and Nd, I think. This is Nd, okay, donor doping. So, what is the accepted doping examiner has given? It is nothing but 10 power 15 per centimeter cube. And donor doping is how much, guys? It is at 10 power 19 per centimeter cube. Okay, fine. If the length of N region is 22 micrometers, very fine. So students, if I say it is a PN junction, guys, if it is a PN junction, okay, now just understand this is P side, okay, and this is N side. Now this is what examiner has given as 22 micrometers. Okay, fine. The length, the width of, or the length of N side, where N side is the length of, if the length of N region is 22 micrometers, okay, and the junction is operated at the reverse bias of 300 volt, okay, reverse bias of 300 volt. Which of the following is not associated with the given P plus N junction under 300 volt reverse bias? Which of the following is not associated for 300 volt reverse bias? Students, a small question I want to ask you. whenever you think about reverse bias, first initially we consider the currents are very small, in the order of nanoamps for silicon, microamps for germanium, and the currents which is a leakage, I say leakage currents. Commonly diode will act as open switch. Am I right? Yes, because we always choose milliampere currents. But when it is going to the limit of a breakdown, because reverse bias is a place where there exists breakdown, when it is moving towards breakdown, there exists a milliamperes current. So for light doping and moderate doping, the breakdown is avalanche breakdown. Commonly the breakdown voltage is greater than 6 volt to around 3000 plus volts also there for power electronic devices. Whereas if the breakdown voltage is in between 1.2 volt to 6 volt, which is happened for heavy doping and extreme heavy doping, that is a Zener breakdown. I think examiner has given 300 volt reverse bias. It's not a joke, very high voltage. Then there exists a breakdown, which is avalanche breakdown. But we have one more breakdown called as early effect, that is a punch through breakdown. Am I right here? One more breakdown called punch through breakdown, where this punch through also happens at very high reverse bias voltage only. This is somewhat tricky. Now what he is asking, which is not associated with the given P plus N junction, which is not associated. Okay, so avalanche breakdown might happens at 300 volt, avalanche breakdown might happens. So it is associated. Zener breakdown, this absolutely not associated, pakka, because it is less than or equal to 6 volt. The breakdown is a Zener. Punch through might be happened. The problem here is even punch through might be happened, might be associated. And the ohmic region, that is highly impossible. So two answers I got fine, but I think either avalanche or punch through, out of both, one must be wrong for the given question. Then how can I find it, sir? I hope you know the logic, dear students. What is punch through here? Commonly what is punch through? Let me say BJT. You remembered or not? In case of bipolar junction transistor. See, for example, it is emitter junction, it is a base junction, right, dear students? Say this is N, this is P, this is N. So it is emitter, right, and it is base, and here we have a collector. Now at a diode voltage, that is collector to base voltage, let me say it is early voltage. Am I right, dear students? It is plus, it is minus. So at early voltage, no doubt, let me say depletion width completely occupies the base. Hello, am I right, everybody in the class? At a specific voltage, depletion width completely occupies the base. That means at this voltage, base current is equal to 0, effective base width WB dash is equals to 0, and base width is equals to depletion width in the base. Base width is nothing but depletion width in the base. And no doubt IC is equals to IE. IC is equal to what, students? IE. IB is equals to 0. Effective base width is equal to 0. This is what exactly happened. That means when you hear the word punch through, there exists a huge currents, which is for sure, it's a breakdown. But depletion width completely occupies the region. Hello, understanding or not? Then now I got a trick. Now I got a trick here. You please find at a 300 volt, you please find depletion width in the N region. I appeal everybody in the class. At a 300 volt, you please find the depletion width of N region. If that depletion width is equal to 22 micrometers, which is the total width of N region, then it is punch through. If the depletion width is not equal to 22 micrometers, if it is below 22 micrometers, then it is avalanche. Because the next step of avalanche is a punch through. Excuse me, am I right, dear students? At punch through is the highest voltage, man, where most of the transistors voltage rating also decided by the punch through only. Okay, so at a large voltage, depletion width completely occupies that specific region. But before that only there exists a breakdown, that is so-called avalanche. Am I right, everybody? So that is very fine. So here, what I need to find, dear students, examiner has given length of N region. Try to find the depletion width of N side. Okay, so have a look carefully, my dear boys and girls. So depletion width of N side. Depletion width of N side. Now respond, it is equals to like 2 epsilon by Q into let me say simply it is nothing but 1 by ND into built-in voltage plus diode voltage, because it is a reverse bias. Am I right, dear students? So students, built-in voltage plus diode voltage, let me say it is almost equal to diode voltage, because it is just built-in voltage is very small voltage, 0.5 volt or 0.7 volt like that. Diode voltage is a 300 volt what examiner has given. And epsilon is nothing but epsilon naught epsilon r of silicon. Epsilon r of silicon is 11.7, or you can take it as a 12. Epsilon naught, 8.85 into 10 power minus 14 farads per centimeters, or minus 12 farads per meters. And a doping examiner has given, ND examiner has given, I think correct or not, dear students? ND examiner has given. So, and length is given, voltage is given. I think everything is specified by the examiner. So this voltage, diode voltage is a 300 volt, and the ND examiner has given, because I am going with only N side. I am going with only N side. Or if you want to find depletion width of both the sides, it is fine. If you want to find the depletion width of P and N together, if you want to find, you can find in that way, no issue about that. Okay, in that case you want to use for both. For example, students, 1 by NA plus 1 by ND. Students, 1 by NA plus 1 by ND. Students, you please let me know what is that. NA is 10 power 15 and ND is 10 power 19. So 1 by 10 power 19 plus 1 by 10 power 15. I think this is very large value, 1 by, if I consider that. In that case, then it is almost equals to 1 by NA you can take. Then this is the depletion width of PN junction you can consider. This is depletion width of PN junction. Hello guys, correct or not everybody in the class? In that case, it is into 1 by NA you can choose, because lightly doped region, and this will be built-in voltage plus diode voltage. I hope you can get the answer now. Okay, so students, if you don't mind, could you please let me know how much exactly you got. Therefore, what is the depletion width here? Anybody in the class, my dear boys and girls, what is the depletion width? So anyways, as per the time being, we have got the answer. We have the answer, dear students. If we could solve, you will be getting almost like a 19.9 micrometers. Oh my god. So the depletion width what we got here is a 19.9 micrometers, and I understand this is lesser than 22 micrometers. 22 micrometers. Hello guys, correct or not? That clearly resembling what, dear students? It is not punch through. If it is equal to 22 micrometers, it is a punch through. So punch through is also not apt for the given data of a breakdown voltage of 300 volt. So Avalanche is absolutely apt for the given data. Therefore, for answers perspective, because as per the answer, which is not associated with the given P plus N junction, no doubt B is not associated, C is not associated, D is not associated. So B, C, D are apt for the given question. Okay, my dear boys and girls, I hope you guys understanding. Yes, you are right. You guys really understanding these concepts. Okay, my dear boys and girls, right? Take care of that. Take care. Very intelligently, examiners framing these type of questions. Okay, now have a look. One more. Time is there, right? Yeah, okay. One more question. Let's have a look onto this one more question, dear students. A MOSFET device has both N-type source and a drain and the drain current. See, the source and drain belongs to N-type. That clearly shows it is NMOS. Am I right, dear students? It is NMOS. Okay, fine. And the drain current flows only when gate to source voltage exceeds 2 volt. That means what? It is a threshold voltage. You're right. Because whenever VGS greater than threshold voltage, then only current exists. VGS less than threshold voltage, no current exists. That too, threshold voltage is positive. Pakka it is NMOS. Am I right? Therefore, threshold voltage is a plus 2 volt. Okay, fine. Whenever threshold voltage is there, see NMOS threshold voltage positive indicates it is enhancement. Hello guys, correct or not, dear students? If threshold voltage is negative, that means even at gate voltage is 0, there exists a channel. That clearly shows it is a depletion, whereas it is enhancement. That means normally off device, whereas depletion is a normally on device. Right, dear students? Take care. So that is enhancement. Which of the following conclusion can be drawn about the device? Fine. The device is N-channel MOSFET, NMOS. Perfect. This is right. It is enhancement type of MOSFET. Perfect. It is enhancement type of MOSFET, right? It has a threshold voltage of 2 volt. Fine, man. 2 volt. And the channel conductance is determined by the hole mobility. No. MOSFET, NMOS, it is a unipolar. It is not hole mobility, it is unipolar. That means only electron mobility. So this is wrong. So 1, 2, 3 must be the right answer. 1, 2, 3. Option B is apt. But commonly, if it is MSQ, this might be giving as options A, B, C, D like that. Then A, B, C will be apt for the given question. Okay, my dear students, right. So let's go for one more very interesting question. Have a look carefully, guys. Consider a MOS capacitor made with P-type silicon. P-type silicon, a capacitor, MOS diode or a MOS cap, P-type silicon indicates what here? It is a silicon and it's a P substrate. Whenever it is a P substrate, it is NMOS. Next. And it has an oxide thickness, TOX, TOX. How much, guys? 100 nanometers. Okay, fine. A fixed positive oxide charge of, okay, I think Q dash oxide. A fixed positive oxide charge, examiner has given, it is 10 power minus 8 coulombs per centimeter square. At the oxide and silicon interface, that means it is nothing but Q dash SS. Whenever it is the case, then TOX is equals to X naught. Am I right, dear students? X naught equal to TOX because it is at the surface. Silicon dioxide, silicon interface, then X naught equal to TOX. Okay, fine. And the metal work function, examiner has given as 4.6 electron volt. So 5M, 4.6 electron volt. It is perfectly, practical MOS cap or a practical MOS diode, right? Assume that the relative permittivity of the oxide is 4. That means epsilon R. Epsilon R for silicon dioxide is how much, my dear students? It is 4. We say 3.9 or 4, fine. And epsilon naught 8.85 into 10 power minus 14 farads per centimeters, we know that. And the flat band voltage, oh, that means the total flat band voltage, which is nothing but 0. Okay. Then the work function of a p-type silicon, we need to find the work function of silicon. So phi silicon is how much? Nice question, dears. So it is a NAT question, very interesting question. So flat band voltage, it is NMOS, nothing but what is, students? Phi ms plus minus Q dash surface states by Cox dash. Am I right, dear? Into X naught by TOX, but X naught is equal to TOX here, so I can avoid that. And examiner has given it as a 0. Nothing but what here? It is phi m minus phi silicon plus, so Q dash, yes, he has given, that is 10 power minus 8 coulombs per centimeter square, whole divided by Cox dash. It is in centimeters. So what is Cox dash? You know that. Cox dash is nothing but epsilon naught, epsilon R of silicon dioxide by TOX. So if I do that product, I told you to remember this, product, right? 3.45, I think. 3.45 into 10 power minus 13 farads per centimeters. Am I right, dear students? Whole divided by TOX. Examiner has given the TOX. Excuse me, true or not, everybody in the class? 10 power minus 11 farads per meters you will be getting, centimeters 10 power minus 13. I think phi m is given by the examiner, TOX given by the examiner. So if we could solve, you are going to get the value for phi silicon. So I hope you can do this. So let me give you the answer. So the answer for the given question is around 4.32 electron volt. 4.32 electron volt. That's nothing but work function of a silicon P substrate from the given question. Okay, my dear boys and girls, right? So like that, you can solve lot many questions, dear students, in MSQ and a NAT based. Of course, in the fixed time slot, what we have, limited time slot. I have solved around some 8 to 10 questions, I think. We'll be solving more questions in our revision series, as we have in the next month, the revision series. So I'll be discussing the entire syllabus in the given time slot, and we'll be solving more questions. I believe you will be getting more conviction if you can go for the revision series. Okay, dear students, and thank you so much, and have a best wishes for your beautiful career. Have a healthy and a wealthy career ahead. Once again, best wishes for your GATE 2026. Thank you.